Welcome to Mr. Bixel's Tutorials. This is the Conservation of Energy Lab Prep tutorial. We have a lab coming up. The controlling question for the lab is this. Is energy conserved for a steel ball rolling down an incline? This assignment's in two parts. First, you need to come up with a plan for this lab and create your own lab sheet that shows what you're planning on doing in the lab. I'm going to be collecting that. This tutorial is going to show what a quality answer might look like. This tutorial also will show you what you need to bring into class on the day of the lab. I would suggest that you simply copy this down and bring it to lab. So, controlling question, is energy conserved for a steel ball rolling down an incline? My tentative answer is my hypothesis. And my hypothesis is yes, it will be conserved. But my hypothesis also includes an explanation of what I think the question means. And I think the question means that energy is the total energy present before the ball rolls down the incline will be equal to the total energy present after within experimental uncertainty. So, the next thing we need is a picture. This is my picture. It shows the event. Here's the ball rolling down the incline and then across the floor. It also shows the things that I'm going to measure. I'm going to need to measure the height. I'm going to need to measure the distance the ball rolls on the floor. I'm going to need to measure the time it takes for the ball to roll that distance. Now, to conceptualize the lab, I'm going to use an energy flow diagram. That's this diagram right here. It's sectioned into two parts, energy before and energy after, and we'll be able to see whether those are actually equal. The system, which contains the objects of interest here, is the ball, the hill, and the earth. What type or types of energy does this system contain before the event? The event, again, being the ball rolling down the hill. Well, I can see right here that it's gravitational potential energy because this ball has mass, it has height, and it's also within the Earth's gravitational field. So I put GPE down. Now, is there any kinetic energy? The ball starts off with a velocity of 0, and since the formulas for kinetic energy all contain velocity, I can safely say that the translational and rotational kinetic energy are 0. The other types of energy, chemical, nuclear, elastic, not really represented in this situation, so we can ignore them. What type or types of energy will it have afterwards? Well, notice that I've put GPE 0. That's because I've made a choice here. I've decided that this line right here is going to be my 0. It's going to be my 0 gravitational potential energy reference. That'll be a height of 0, so when the ball's along that line, it'll have 0 gravitational potential energy. You might remember that from Energy Skate Park. So, what equations am I going to use? The total energy before equals the total energy after. Notice the question mark. I can't assume that that is actually equal. The question mark is there to show that I'm testing to see whether the total energy before is actually equal to the total energy after. So the total energy before is calculated out. That's just GP. We use MGH. Total energy after, it's translational plus rotational. There are those two equations. When I put them together, that's 1/2 plus 1/5 mv squared, which equals 7/10 mv squared. That's right there. Now, if you look at the equation right here, this is mathematically what the lab's all about. So the only thing left to do as far as preparation work is figure out how we're going to measure the different quantities in this equation. We're going to need to measure the mass, the height, and the velocity. Now we can't measure velocity, but we do know that if we take distance divided by time, that equals velocity. So actually we're going to have to measure the mass, the height, the distance, and the time. And it's important that we identify the things that we have to measure, because those are the things we're going to have to do in lab. Now, let's start off with a measurement of height. right here. I think I'll measure my height one time. That'll give me a best value. And then to get the uncertainty, I'll just do sum of acceptable uncertainty. That'll give me my best value and my uncertainty for height. Notice I have this table for sources of acceptable uncertainty all set up. Next, mass. Same thing. I think I'll measure my mass once in a triple beam balance, and then use source of acceptable or sum of acceptable uncertainty to get my uncertainty for the mass. For the distance on the ground, same thing. I'll measure that once, and then use sum of acceptable uncertainty to get my uncertainty. And then finally, the time. I'm going to let this ball roll this distance about 5 times. That way I can average my times and get my average, and I can use my calculator to do standard deviation similar to average deviation to get my uncertainty. Then I'm completed with my measurements. From there on out, it's all calculations. And the reason I haven't done the calculations is because I don't have the data yet. But it's just going to be finding my gravitational potential energy and the uncertainty and the total energy after with the uncertainty. So this is going to look like this. GPE max equals mass max plus gravity max plus height. Maximum equals, and then the numbers are going. And for gravity, we're just going to use 9.80 plus or minus 0.01 newtons per kilogram. And we've got GPE best value equals the best value we have for mass times the best value we have for gravity times the best value we have for height. I'm not even going to put in the translational kinetic energy because I'm not sure how much space I'll need down here to finish out the gravitational potential energy, but this constitutes a good solution to the homework where you were to plan the lab, and it also constitutes a great lab sheet to bring into class on lab day. Thank you for watching. This has been Mr. Bixel's Tutorials.